Since the 1930s, scientists have discovered evidence suggesting that an enigmatic type of matter that manifests itself at various scales accounts for around 85% of the mass of the universe. There are several theories as to where this component came from, but physicists have not yet reached a firm conclusion. The enigmatic substance is known as dark matter since it does not emit light. Along with stability and disappearing electric charge, observations also call for dark matter particles to have a very long lifetime. Because particles are often detected through electromagnetic and strong interactions, which are typically considerably more intense, it is exceedingly challenging to examine dark matter experimentally because it interacts with other particles only through gravity and possibly through weak interactions. Thus, despite several attempts using ground-based detectors, particle colliders, and satellites, no components of dark matter have yet been discovered. However, astronomers have been deeply researching this issue and have put out a wide range of potential dark matter candidate particles, some of which are outside the purview of the standard model of fundamental particles. These include hypothetical primordial early universe black holes, massive particles with weak interactions, ultralight axions, and many more. Could gravitons be a good dark matter candidate? Researchers proposed a very intriguing theory a few years ago, positing that the basic elements of dark matter might be compact arrangements of gravitons connected to one another by gravity. This hypothesis is particularly appealing because, unlike many other theoretical models of dark matter, it does not ask for the consideration of unidentified particles. Simplicity is often a key factor in physics. Their research, however, was flawed since general relativity is recognized to be an incomplete theory of gravity because it does not account for quantum processes. There is enough quantum gravity theory that is now widely accepted, although researchers have created a lot of potential alternatives. Researchers refined the analysis by taking into account graviton interactions in several quantum gravity theories, string theory being the most well-known example. Through analytical calculations, physicists have discovered that gravitons can in fact attract one another and form compact objects that can serve as dark matter in practically for all the theories they studied. These objects were given the name Planck balls because, according to the scientists' calculations, they were of the order of the Planck length, a unit of measurement that is common to all theories of quantum gravity and is roughly equivalent to 10 to the minus 35 meters. The energy of gravitons needed to be very high for the production of Planck balls, usually of the order of the Planck mass, a typical quantum gravity mass scale that is around 22 orders of magnitude heavier than an electron. It implies that bound graviton systems could only have developed in the very early universe, where the temperature was extraordinarily high. In some theories of quantum gravity, it is of the order of 1032 degrees. Even though the theory behind the researchers' idea is very intriguing, only more exact experimental studies in the future will be able to tell which of the various dark matter theories is true or whether the reality is even more complex, and dark matter is made up of particles that scientists haven't even thought of yet.